discuss about the multirate digital signal processing in digital signal processing. Multirate digital signal processing mainly consists of rate conversion, sampling rate. So down sampling, up sampling, we call it as the decimation, interpolation, how a digital signal from rate to another rate conversion is happen. In single rate conversion, we are using only one sample frequency. But in multi-rate signal processing, we are converting from one sample frequency to another sample frequency rate. So this is the scenario in which, for example, sampling rate conversions, various types of studios in various countries, we are using different types of sampling frequencies. For sample rate conversion from one country's studio developed concept, whether it is a video stream or some digital signals that should be broadcast in another country, it should be matched with their country's sampling rate conversions. For example, CD conversion to a particular studio signal processing, it rates from 44.1 kHz to 48 kHz. So this is the main scenario for. So what is a multi-rate signal processing? Means multiple sampling rates. A multi-rate DSP system uses multiple sampling rates within the system. So the process of converting a signal from a given rate to a different rate is called as sampling rate conversion. A system that employs multiple sampling rates in the processing of digital signals are called as the multi-rate digital signal processing. So for example, professional audio systems in various countries, we are using 48 kHz rate, but consumer CD plays as 44.1 kHz. And some countries they are using 32 kHz. So that's why it is the conversion rate is from one level to another level is desired. So that's why multi-rate signal processing is mandatory for one conversion to another conversion of digital signals. So not only signal conversion, so multiple sampling rate can be used to compress the signals, which saves the bandwidth as well as storage space. So signal compressions, image coding techniques, speech coding techniques, analog to digital conversions, digital to analog conversions, and all communication systems, we are adopting the multi-rate digital signal processing. So there is a various types of requirements are there. Computational requirements are very less. Storage for filter coefficients are less. Finite arithmetic effects are less. So that is the advantage of finite arithmetic mathematics. Filter order required in multi-rate applications are low. Sensitivity to filter coefficients lengths are also very less. So while designing multiple rate of systems, effect of aliasing for decimation and pseudo images for interpolations should be avoided. So there are two types of broad techniques. One is called the upsampling, another one is called as the downsampling. Third is the hybrid technology, that's we called as the resampling. So first one is the decimation or downsampling to decrease the sampling rate. Second one, interpolation or upsampling to increase the sampling rate. Resampling to continue and combine the decimation and interpolation in order to change the sampling rate by a fractional value that can be expressed as a ratio. For example, I want 1.5 rate of conversions. Then upsampling by 3 times and downsampling by 2 times, so that it is equal to 3 by 2, that is equal to 1.5 times conversion. This also happens with resampling techniques. So this is the scenario for M-fold decimator as well as L-fold expander. M indicates for the decimation, L indicates for the interpolation. So upsampler is used to increase the sampling rate by an integer factor. Similarly, downsampler used to decrease the sampling rate by an integer factor. So this is the scenario for upsampler, time domain characterization. An upsampler with an upsampling factor L, where L is a positive integer, develops an output sequence XU of n with a sampling rate that is L times. So in upsampler, we are adding some number of zeros for each and every two samples. L minus 1 number of samples are considered as zeros that are inserted between the every two samples. That means that every Lth sample is to be considered. Between each and every L sample length, we are adding L minus 1 number of zeros. Upsampling operation is implemented by inserting L minus 1 number of equidistant zero valued samples between two consecutive samples of x of n. So in the mathematics, so x of n by L, so n is all integer multiples of 0 plus or minus L plus or minus 2L, etc. So this is the scenario in pictorial representation of upsampling. So where the particular upsampler, the signal is existed, we are considering each and every L number of upsampler. So between that, so every samples between each and every L samples, between that we are inserting zeros. In practical scenarios, we are inserting some non-zero values in between these L samples. In practice, the zero-valued samples inserted by the upsampler are replaced with appropriate non-zero values using some type of filtering process. Process is called the interpolation and will be discussed in next class. Next one is the downsampler. Time-domain categorization. A downsampler with a downsampling factor m, where m is a positive integer, develops an output sequence y of n with a sampling rate that is 1 by mth of that of the input sequence x of n. In block diagram, so just observe this down arrow indicates that this is the decimation downsampler. That means that this is the m times. That means, for example, if m is equal to 2, so every second sample I am considering. If m is equal to 3, every third sample we are considering. That means that if m value is equal to some number, so that particular integer number samples only considered. Remaining all are to be we are just deleted the particular list. So downsampling operation is implemented by keeping every mth sample of x of n and removing m minus 1 in between the samples to generate y of n. So y of n is equal to x of n into m. So this is the pictorial representation. So just observe in the input sequence, there all types of samples are available. In between these particular samples, these particular samples, so we are considering only the Lth. What else? Suppose L is equal to 3. So that means that every third sample is only remained in the list. So between that, so whatever number of samples are there, that all are removed. That's why minimum number of samples are required to reconstruct the original signal. So that means that minimum space is sufficient. Minimum bandwidth is sufficient to transmit the digital signals. So this is basic sampling rate alteration devices. So sampling periods have not been explicitly shown in the black diagram representation of the upsampler as well as downsampler. This is for simplicity and the fact that mathematical theory of multirate systems can be understood without bringing the sampling period t of the sampling frequency ft into the picture. That means that x of n is equal to xa of nt. So this is the down sampling with m number. Y of n is equal to xa of n into m of t. So if the input sampling frequency ft is equal to 1 by time period, then output sampling frequency ft dash is equal to ft by divided by m. That is equal to 1 by t dash is the time period. So figure below shows the explicitly time dimensions for the upsampler. So x of n is equal to x of a into n of t. So this arrow indicates the upsampling y of n. So in upsampling, the frequency and the time period ft is equal to 1 by t. In output sampling frequency ft dash is equal to L times ft, that is equal to 1 by t dash. That means that frequency is increased in upsampling and the frequency is reduced in downsampling. So this is the in multirate signal processing. We have broadly two methods. The first method is the upsampling. Another second method is the downsampling. Upsampling is also called interpolation to increase the digital rate. In downsampling, this is also called as decimation to reduce the number of samples required and also the frequency rate. So different types of conversions for analog to digital conversions as well as digital to analog conversions happens with this upsampling as well as downsampling in multi-rate signal processing. Thank you.